Welcome back, and the topic of today's video is going to be colligative properties, which are a set of solution properties that depend upon the number of solute particles per amount of either solution or solvent. So in other words, these are properties that are going to depend upon solute concentration in one form or another. So as we go through the various colligative properties, you're going to see some of the various concentration units that we've been talking about up until now. So let's take a look at some examples of colligative properties, and then we'll come back and look at an example or two of a numerical problem involving colligative properties. So the first colligative property that we want to talk about is one that we've actually dealt with before in class. It's sort of our first colligative property, and it's based upon Raoult's law, which we have already talked about and seen in class. And this is vapor pressure lowering. So the idea here is that if I were to add a non-volatile solute to a volatile liquid, the vapor pressure of the solution is going to be lower than that of the liquid by itself, which we've already seen. And the equation for describing this is going to be this form of Raoult's law, where we say that the vapor pressure of the solution is equal to the mole fraction of the volatile component, which is the solvent, multiplied by the vapor pressure of the pure solvent by itself. That's what the P naught here represents. And again, we've seen that situation already in class. So that's our first basic colligative property. The second one, which is also very useful to us and probably one of the most useful colligative properties in science, is osmotic pressure. Now this is a topic you've probably explored before, for example, in a basic biology class. And what osmotic pressure deals with is a pressure differential which exists on either side of a semi-permeable membrane, as I've shown you here. So what we have here is a set of two compartments, a compartment that contains only solvent, and another compartment that contains solvent and solute, which are separated by this semi-permeable membrane. Semi-permeable here means that certain species can pass across the membrane and others cannot. So the assumption here in our case is that solvent can pass back and forth across the membrane, but the solute molecules or particles cannot. So what happens in a situation like this is there's generally going to be a force that's going to allow toward dilution. We want to have dilution occur. So we have obviously a more concentrated side over here on the right, a less concentrated side of pure solvent here on the left. So the general tendency is toward dilution. So what's going to happen is solvent molecules are going to pass across the semi-permeable membrane in an effort to dilute the solvent plus solute side. As a result of that, the level of the liquid on the left-hand side is going to drop, while the level of the liquid on the right-hand side is going to rise. And that's going to correspond to a height in a set of water columns, which we can then, based upon your knowledge of bonding, relate back to a pressure. So this is why we call this an osmotic pressure. Now, the degree to which this pressure differential exists is going to depend upon the concentration of the solute over here on the right-hand part of this device. So ultimately, we can express this in terms of a pressure here using this equation, which looks an awful lot like the ideal gas equation. So this looks a lot like PV equals nRT. The only difference here is that the pressure in this case is going to be a capital Pi, and that's going to be the osmotic pressure. All right. Otherwise, this is the normal volume that we talk about. This is the normal number of moles. R is the normal gas constant that we would use in PV equals nRT, and T is going to be temperature. And of course, we have to make sure that we use the correct units throughout that correspond to the units of R that we're going to use here. So which R do we want? Well, we want the PV equals nRT R. So in this particular case, R is going to take the value of 0.08, what is it, 206 liter atmospheres per mole times Kelvin. All right, so that makes a situation here where volume needs to be expressed in liters and needs to be in terms of moles, T needs to be expressed in terms of Kelvin temperature, and pi, of course, will be in terms of atmospheres to make everything work out. Now, there's a few other ways that you sometimes see this equation written. We can rearrange the equation here to bring the v to the other side, where we end up with ratio of n over v. Now, if we look at this, n is in terms of moles, v is in terms of the total volume of the system. Moles per total volume is equal to molarity, so we sometimes also see the expressed as pi equals to molarity times r times t. So that's another way of expressing this particular equation. Then the last set of colligative properties we want to discuss are more or less interrelated to one another. And these are boiling point elevation and freezing point depression. So the BP here stands for boiling point, the FP here stands for freezing point. All right, so essentially what's happening here is if I add a non-volatile solute to a liquid, what's going to happen here is the boiling point will be elevated relative to the boiling point of the pure solvent, and the freezing point will be depressed relative to the freezing point of, again, the pure solvent. So the equations that we use here are quite simple. This delta here represents the actual change in boiling point between the normal solvent boiling point and the solution boiling point. All right, so we're going to see how to use this here in just a little bit. But if I want to see the magnitude of the boiling point elevation, I can use this equation, where Kb is a constant. We call it the boiling point elevation constant. And we multiply this by the molality, little m, molality of the solute. All right? The freezing point depression works more or less the same way. This again represents the magnitude of the freezing point depression. So in other words, this is the difference in the freezing point between the solution and the pure solvent. Now, also, that's equal to a constant. In this case, the constant is called a freezing point depression constant, and we multiply that by the molality of the solute. Now, because the equations are more or less the same, the two constants are going to have the same units, and those units are going to be degrees Celsius per molal. So, what we're going to do next is we're going to come back and take a look at a couple of numerical examples in which we can use these colligative property equations.
Go.
All right, so let's take a look at an example of a typical kind of problem that we might work using colligative properties. So one of the primary applications of colligative properties is in the determination of the molecular weight or molar mass of an unknown compound. All right, so this is an example of that type of calculation, and we often use osmotic pressure to make these kinds of measurements. So this is an example from your example sheet that I gave you in class. And in this case, we have an aqueous solution consisting of 10 grams of catalase, which is an enzyme found in the liver. And it has a volume of 1 liter, this solution does, at a temperature of 27 degrees Celsius. So it says here the solution's osmotic pressure was experimentally found to be 0.745 torr. And we want to calculate the molar mass of the catalase. Now, to get molar mass, we need two things. We need to know the mass of the enzyme, and we need to know the number of moles that correspond to that mass of the enzyme. So we're in pretty good shape here because we've already got the numerator. The problem tells us that we have 10 grams of the enzyme. So we have the numerator here. Okay, but what we don't have is the denominator to get the molar mass. So this is where we're going to use osmotic pressure, our colligative property of choice. Now, since we want to get moles, what we're going to do is take the pi v equals nRT equation and solve it for n, since n is moles. So when we do that, we see that n is equal to the osmotic pressure times the volume divided by r times t. So now, the next thing that we have to do is we have to go back and make sure that our units are in good shape. Because again, we have to make sure that we are working with the correct units of r here. Now remember, r in this particular case is in terms of liters, atmospheres, per mole times kelvins. All right, so that means that all of our units that we're using here have to be in terms of those specific units. So let's see what we have. Liters look like we're okay. We've got liters here for volume. Osmotic pressure, though, what do we need here? Well, I've got torr, so I need to get from torr to atmospheres. So we need a conversion to do that. So we're going to go off to the side and take care of that. So I've got 0.745 torr. That's my osmotic pressure that I measure. And I want to convert that to atmospheres. All right, so we need a conversion factor to do that. We know that 1 atmosphere corresponds to 760 torr. You'll remember that hopefully from bonding. Now, notice that torr will cancel with torr, and I've got this worked out someplace. This turns out to be 9.80 times 10 to the minus 4th atmospheres. All right, so we've got pi, we got V, we know what R is, but we still need a temperature. Temperature is 27 degrees Celsius. Now we need to get that to Kelvin. All right, so we know how to do that. So I'm going to take my 27 degrees Celsius here, and I'm going to add to that 273 Kelvin. And that'll take me to my Kelvin temperature, and that turns out to be 300 Kelvin. So now I'm in a position to go ahead and substitute everything into my osmotic pressure equation solved for moles. All right, so let's do that. Pi is 9.80 times 10 to the minus 4th atmospheres. Volume is 1 liter. That's given in the problem. No conversions necessary. I need R down here in the denominator at 0.08206 liter atmospheres per moles times kelvins. And I need T down there expressed in kelvins. That's 300 kelvins. And let's make sure that we actually get mole units out of this. All right, so atmospheres will cancel here. Liters will cancel here. Kelvins will cancel here. Notice that moles is in the bottom of the fraction. So that's a complex fraction. So moles then comes to the top. So if I work this out, my N turns out to be 3.98 times 10 to the minus 5th moles. All right, now I'm not done yet. I've got my moles now, and I've got my grams. I still need my molecular weight. So let's go ahead and calculate our molecular weight. So my molecular weight is equal to the 10 grams of the catalase that I started with, divided by the corresponding moles, which we have calculated here. 3.98 times 10 to the minus 5th moles, and to 3 sig figs, that turns out to be a molecular weight of 2.51 times 10 to the 5th. And you might look at that and say, well, that seems like a really, really large molecular weight, but keep in mind that an enzyme is an example of a protein, which is a very large biomolecule. So we'd expect to see very large molar masses associated with things of this nature. So this is a good example of how to use a colligative property to determine a molar mass of an unknown compound. All right, so let's take a look at one more simple example using colligative properties. In this particular case, this is a freezing point depression problem. So what we've got here is a situation where we want to know what the freezing point of a solution prepared by adding 5 grams of sucrose, which is table sugar, and I give you the molar mass of it here, to 100 grams of water would be. Okay? So since I'm adding a non-volatile solute to a solvent, I would expect the freezing point to be depressed. All right, so in a situation like this, here's the general equation we want to use. So this gives me the magnitude of the freezing point depression. That's equal to the freezing point depression constant times the molal concentration of the solution. Now, what I have to normally do in a case like this is to go look up that freezing point depression constant, which I did. Those are generally going to be found in tables in your book. Now, the freezing point depression constant is going to be dependent upon the solvent. So in this particular case, the solvent is water. So I would go and look up the freezing point depression for my particular solvent, which is water, and I find it to be 1.86 degrees Celsius per molal. All right, so now that I've got the KF for my solvent, I can use my freezing point depression equation to calculate the delta T. Now the first thing I need to know though is the molality. All right, so let's go back and remind ourselves of what molality in this particular case is. Little m is equal to the moles of the sucrose, which I'm just going to abbreviate as SUC, divided by the kilograms of the solvent, which in this case is going to be water. All right, so I need to be able to get these two values to be able to calculate the molality. Now I can do that because I have a mass of the sucrose. So let's go ahead and work from that point of view. I've got 5.00 grams of sucrose, and I want to convert that to moles to get a molality. So I know that 1 mole of sucrose has a mass of 342.29 grams. All right, so grams of sucrose will cancel with grams of sucrose, and I'm going to end up with a value of 0.0146 moles of sucrose. Again, that's going to be good to 3 sig figs. Now, at this point, I can go ahead and calculate a molality. We'll make the conversion of grams to kilograms in our head in this particular case, not too hard to do. So my molality is going to be 0.0146 moles of sucrose per, converting my 100 grams to kilograms, that's going to be 1/10 of a kilogram of water. And when I do that calculation for molality, I'm going to get 0.146 molal. All right, so that's the molality of the sucrose in water. So now I'm in a position to come back around and calculate my magnitude of my freezing point depression. All right, so I'm going to take my constant, which is water specific. So that's going to be 1.86 degrees Celsius per molal. Multiply that by the molality, which I have here, 0.146 molal. We see that the molals cancel, and what I'm going to end up here with when I do the calculation is 0.272 degrees Celsius. Again, to 3 significant figures. Now keep in mind that this value is the magnitude of the freezing point depression. What the question actually asks us for is what is the freezing point of the actual solution. So we actually have to calculate that from the delta T sub F. So the T of the solution, that's the freezing point of the solution, that's going to equal to the normal freezing point of water, which is 0 degrees Celsius. That's where pure water normally would freeze. And I'm going to have to subtract from that the magnitude of the freezing point depression, because it's a freezing point depression. We expect the freezing point to be lowered. So I'm going to subtract from that the 0.272. And what I'm going to end up with for the freezing point of my solution is minus 0.272 degrees Celsius. And that's a very typical example of the type of problem that we might see using either boiling point elevation or freezing point depression.